Hi, today we're looking at GrayCode. Let's break this problem down in a way that makes sense. Before we get started with this problem, there are two important points I want to mention. One, do not look at the most posted solution for this problem because it uses some other approach other than backtracking. And two, this is a backtracking problem with two very important takeaways. We'll look at them in the approach section. Let's start. Let's start with looking at the race framework that we'll use to solve this problem. So RACE stands for Reason, Approach, Code, and Evaluate. We have a complete video created about the explanation of this framework. Look on the top right, there should be a link, click it and look for more information. Even if you do not look at that video, I'm sure it should be okay to follow along. Let's start with reasoning with the question, so which is R in our RACE framework. Let's start with reading the question and see what it asks. So the question says that an n-bit gray code sequence is a sequence of 2 to the power n integers, which means if n is 2, a gray code sequence will be a sequence of 4 integers, which is 2 to the power 2. So in that sequence, we have to follow these rules. Every integer is in the inclusive range of 0 to 2 to the power n minus 1, which means if n is given as 2, then the sequence that we have for the gray code will have 0, 1, 2, and 3. So 0 to 2 to the power n, 2 to the power n minus 1. And the first integer given to us is 0, so that's great. That will be our starting point. An integer appears no more than once in the sequence. Okay, so we have to use each candidate just once. So it'll essentially be a permutation of 0, 1, 2, 3, where we can use one number just once. The binary representation of every pair of adjacent integers differ by exactly 1 bit. So this is a very important point. What they say is that if two integers are adjacent to each other, they should differ exactly by 1 bit in their binary representation. So that means if the first number is 0, which is 0, 0 in binary, the second number can be 0, 1 because they differ by 1 bit. It can also be 1, 0, which again differs by 1 bit. So either it is 1 or it is 2. Okay, let's continue reading. So the second condition it says is that the binary representation of the first and the last integers differ by exactly 1 bit. So that's also important. So the first and the last bit, that also has to differ exactly by 1 bit. To be honest, when I first read this problem, I was also a little intimidated because this sort of brings the bit manipulation in picture. Bit manipulation is one of those topics which is not very frequently asked, and it was also at the same time very difficult to remember. But I still went ahead and looked at this question because it does carry very two important takeaways of backtracking. So I would request you to follow through and at least look at the approach section to get those two important points about backtracking so that you can apply them to other problems. Okay, so given these 5 points, let's start. The very first observation we want to make is that the first integer is 0. So let's just write that down. The second observation would be that whatever comes after 0 has to vary by exactly 1 bit in its binary format, which means if it's 0, 0, it can either be 1 integer 1, which in its binary format is 0, 1 and varies by 1 bit, or either it can be 2, which in binary format is 1, 0 and can vary by exactly 1 bit. So now given that, the second observation would be that we want a recipe to generate these numbers. So we need a recipe to generate adjacents satisfying the given constraints. Let's focus on the second observation for a bit. We know this problem involves some form of bit manipulation. So let's take a quick sidebar and understand two concepts to be able to derive a recipe by which we can generate adjacent numbers after 0. The two things that we'll need to tackle the second observation here. So let's quickly take a sidebar here. The very first thing we'll need is bit shifting. The second thing we'll need is understanding the XOR gate. So two of the very important concepts. If you learn them anyways, you'll be able to solve many more questions. Let's start with the first one. So bit shift. Here we'll specifically be looking at left bit shift, which means that given 1 and you shift it by 1, what do you get? So 1 in binary is 0 1. When you move 1 bit left, you get 1 0, which is 2. So in a sense, moving any element by 1 is equal to multiplying with 2. That's also how you can say it. So which means if I shift 1 bit by 2, you will get 1 0 0, which is 4, which can also be written as 1 into 2 to the power 2. So that's that. Let's go on and understand what XOR is. So a fun way to understand about XOR is if you just call it the drama gate. Why I call it a drama gate? Because if it sees everything uniform, so if it sees 0 and 0, which are same bits, or 1 and 1, it doesn't react. But if it sees differences, that is when the XOR reacts. And this is what the XOR gate is. Easy. So if you just remember these two things, we are in a very good position to start looking at the approach for this problem. Let's move on to discussing the approach for the question. So we are in the approach section now. Let's think about the example that we just was given to us, which is n equals to 2. We know that our starting point is 0, which in binary is written as 0 0. And since n is 2, we can generate two numbers. The numbers that we generate here is precisely where we use the two concepts we just discussed. So you can get a 1 bitwise, exactly 1 bit difference number when you XOR the number with a mask. So if you want to create difference in the 0th bit, you just create a mask of 0 1 and XOR it with that. Now see the magic here. What we learned was that if XOR gate sees no drama, which is 0 0, it doesn't react. As soon as it sees differences, it reacts. So you get 0 1, right? So let's say here we XOR with 0 1, and on the right 0 0. If we move our mask bit to the left, so if we XOR it with 1 0, we see drama, we'll get 1 and 0. So you get two numbers here, 0 1 and 1 0. Now a recipe to generate this mask is where we use our bitwise operation. So if you look closely now, we used two numbers to create the mask, 0 1 and 1 0. This 0 1 is 1 shifted with 0. So if you do not move the bit anywhere for 1, and you'll get exactly what we have, which is 1. If you move the bit by 1, you get 1 0, which is 2. So this is 2 and this is 1. So all you have to do is you just use this 1 moved n, and n goes from 0 to 2 to the power n minus 1. Or if the given n you have, actually let's call this k. So the n that you have, if n is given 2, you just go 0 to 1, which is 2 minus 1. If you just use the simple range operator here, it will take care of that. But the point to take away here is that k will vary from 0 to 1. And if you just use this, you'll create a mask. And you just XOR that mask with your current number to generate the valid next integers which satisfy the constraint of exactly 1 bit difference. So once we get that down, we can proceed and complete the tree. So here we have 0 1, which is also called 1 in the integer world, and you have 0 1. Either you XOR it with 0 1 or you XOR it with 1 0, which is your 1 moved once. Here 1 was moved 0 times. So k is 0 here, k is 1 here. And if you XOR this, again, all the bits match. So there is no drama and you will get 0. Here, you look at the first two bits, there is a difference. You get 1. Again, there is a difference, 1. Remember, XOR is the drama gate. It sees a difference, it reacts. Again, we keep going. Before we keep going, look at this now. You have already seen this. That's where we started. And so this becomes a loop. So this is another very important observation that we have to make, that before branching out, we have to check if we have seen the element again or not. So we need a scene sort of a data structure here, which will tell us that the current element that we have generated, that element should not be one of the scene. So here, if you go down this path, 0 0 is where we started with. So this becomes a terminal case for us. Okay. So if this becomes a terminal case, we carry on and go with the right. So again, we XOR 1 1 with 0 1, we XOR it 1 0. We look at the bits, no drama. I mean, yes, drama. So we'll have 1, and 1 1 means no drama. We'll have 0. Here again, 1 1 is no drama, which is 0 and 1. Here you get 1 0, you get 0 1 here. Again, this 0 1 becomes a red case because you've already seen 0 1. So this becomes a loop again becomes a terminal condition, right? And whereas this 1 0, this is our 2, this was 4, this is 1, sorry, this is not 4, this is 3. So this is one solution set you got, which is 0 1 3 2. The question asks to just give you one solution set. So as soon as you get a solution set, you can just terminate and say that you found the solution. But we have to really take notice of this, where there is really a loop here. This is no longer a unidirectional exploration that we're doing. This sort of becomes a graph because it loops back into one of the elements that we have already seen. So we'll need a scene data structure. All right, I think we have everything covered. Let's now jump into the code section. All right, let's get started. So let's start with some housekeeping. We'll have a ans variable, which is the answer variable to collect our final answer. And then we will have a backtrack. So in our backtrack, we'll have these variables. We'll have n. So n is the given n, right? We'll have current num. So this becomes important because we'll have to start creating calls from the current num. We'll have a current answer, which is our state variable to retain the current answer. And then we'll have a scene variable. Scene variable is important because we want to keep track of the loops. Okay. With that, let's look at the part where we'll generate candidates given our current number. So here, as we discussed, that we create the candidate as per n. So the use case that we discussed was n was 2, and we want to shift the variables for 0 and 1, which is 0 to 2 minus 1. So that's precisely what we'll do. The next number that we can get given n is, we'll just take the current number, exactly what we discussed. We'll take the current number, we'll XOR that number with bitwise shifted with I. So here, for example, if the current number is 0, it will be shifted with 0 XOR. So the XOR is our drama gate, if you remember. And then we'll have 1. We'll generate 2 candidates here, where I will take the value of 0, which is shifting 1 by 0, which is, it'll XOR 0 0 with 0 1 once, and then it'll XOR 0 0 with 1 0. You'll get 1 0 when you shift 1 with 1 place, which is 1 here. Okay, so given that, the very first thing we'll do is we'll first check if we have already seen this element. In case we have seen this element, we'll prune and not make a call. So we'll continue. If we have not seen this element, what we do is we further recursively call backtrack. N will be passed as it is. Current num will be the next candidate, the next number we just generated. Current answer. Now, current answer it can be added like this. So here, I am keeping the answer in the current state. State means when my tree will be created, my answer will be retained in the state, and it will not be available in any other call. But if we do this in this question, it will run into MLEs. So some of the test cases really are of the kind where the tree that you create will be huge, and therefore this will MLE. It will run into memory limit exceeded. And therefore, what we do here is we'll use the actual backtracking pattern, where we'll say current, we actually append it. So now current answer becomes our global variable, and we'll use it as a global variable. We'll create 1 when we call the backtrack, and we'll use the same variable between all the recursive calls. So which means that you have to append it, and then once the call is done, we have to remove it. So you just say pop, and you have to remove the 1 at the end. So you just say pop minus 1, right? This makes it explicit, and it's for me at least, it's a little less confusing. So if you write minus 1, it becomes more clearer. Similarly, once an element has been called, and you know that it's not in scene, we have to add it in scene. And again, once you backtrack, that is, once you're done considering the element, you have to make sure that you remove it. So these two calls are sort of similar, right? Okay. So after next, the next thing that we do is current answer. So we'll pass current answer as it is, seen as it is, because we've already added our next element in them, and we'll give the call to self backtrack. Now, one thing that we have to do here is, since the answer is only asking us to return one possible answer, so the question just says that we want one possible answer. So as soon as we get the result, so if result, we return true, saying that we found the result, right? So this is important so that we don't keep looking for more results. If we do not get a result here, we return false. All right, I think that's it. Next, we just backtrack, and let me quickly copy paste this. So here n remains the same. Current number, we are given that the first integer is always 0, so we start with 0. The current answer will have 0, right? And similarly, since 0 is already seen, we'll add 0 in our scene here. Okay, that's that. And you just return self dot answer. Okay. Okay, so you might very well see that we missed the terminal condition here. So the terminal condition is also very straightforward. If you just say that if your current answer, if that becomes equal to 2 to the power n, so if n is 2, your answer length will be 4, and you can notice this. And okay, so that's important. So once we get this, we just say self dot answer equals to current underscore answer. So use of current ans as a global variable. So if you don't copy it here, it'll get changed in the subsequent calls and you'll not get the right answer. So please make sure that you have copy here. So here, so this is a very important point. So you have to copy because current ans is globally shared between recursive calls. All right, we have the terminal condition in place, and we have our loop detection in place, and we are making sure that we are cleaning our variables. And if we get an answer, we return. All right, I think that should do it. Let's run this and see. All right, looks like this was accepted, 1 and 2. Let's just test it for a bigger case, let's say n8. And how about we test it for 15? Another test case, we test it for 16. So we have 1, 2, 8, which is an even number, 15 odd, and 16. And n can go from 1 to 16. So if this works, we are sure that it will submit. It's always good to perform your own sanity checks. If this works here, we can go ahead and quickly submit. It looks like the time limit exceeded. Oh, okay. So this is one. So we did not really, return true. Once you find the solution, you have to return true. So that's sort of becomes very important. Now, if you run that, this will make sure that after hitting the terminal case, it will not keep calling. All right, perfect. Okay, looks like that worked. Now dive back and look at our evaluate. I hope that helped and made sense. Let's just quickly mark our code section as complete. Let's move on to look at the evaluate. Okay, so if you think about the time complexity here, it will be O n into 2 to the power n. We say 2 to the power n because you are moving the bits 2 to the power n times, and you'll do that for each number. So the time complexity becomes n into 2 to the power n. Space complexity, we are retaining the scene, and we are also retaining the intermediary results, though we are popping them out every time. So thanks to that, the space complexity will still be n, because at any point of time you will have the recursion stack, as well as you will have n elements in these data structures. So the space that you occupy will be directly related to n, which is given to us, and it will be O of n. I hope that this made sense, and I hope that this also gave you a clear understanding of where backtracking starts to show itself. All right, that's a wrap. Thank you so much for sticking around with me up until here. On the way, we were able to understand two very important concepts of bit operations. It never hurts. So thank you so much for watching, and see you in the next one.